This is chapter 4, performance evaluation, in the subject parallel and distributed computing for second year engineering students in the Higher Institute of Medical Technologies of Tunis. In this chapter, we will talk about some evaluation metrics to evaluate parallel systems. Mainly, we will talk about communication overhead, speed up or acceleration, efficiency, scalability, and fault tolerance. So let's start with the communication overhead. We talked in chapter 2 about communication tools and communication topologies. Now we will quantify this. So the communication, let's take some metrics first. Consider this is a node and a message will be sent to this node. We have the latency, bandwidth, la bande passante, the size of the message, and the time needed to send the message. The latency is the time it takes for a message to travel from here to here, not including the size or the bandwidth. It's like we are considering an empty message. Latency is the time needed to send empty message. After that, this is the latency. After that, we can add the second term, which is the size of the message divided by the bandwidth, which represents the time it takes to transfer the message at the available network. You can see that the size of the message is in the numerator, so as much as the size of the message is high, as much as the time it takes to send the message is high. But for the bandwidth is in the denominator, so as much as the bandwidth is high, as much as the time is less. This is the philosophy of calculating the time needed to send the message. It depends on it has two parts. The first part is the latency, not dependent to any thing related to the size or the bandwidth. It's the time needed to send empty message. And the second part is the part related to that specific message. We need its size, we need the bandwidth used to send this message. This is in general. We will need these terms to quantify the metrics in this chapter. Okay, so now what's the purpose? The purpose is to evaluate the communication cost when sending a message M of size N from a processor Pi to a processor Pj with the number of links between Pi and Pj being H. Yani whatever the topology, 2D grid, 3D grid, hypercube, etc. We don't care about the topology in this chapter, but we care about the path اللي مشيت فيه في وسط هاك التوبولوجي هذيك. الباث اللي مشيت فيه هذايا فيه H هي number of hops. H is the number of hops. How many hop عرضتنا في الثنية واحنا ماشيين. So the first and the easiest way to do that is to send the full message once at a time. Send the M, the complete M, from one step to the next through the intermediate processor. So I want to send this message from processor PI to processor PJ. Here I have 1, 2, 3 hops. So in the first step, I will just send the message M from PI to one of the intermediate hops. After that, in step 2, I will send the same message to the next node. Then to the next node. حتى لين في step 4 I will then reach my destination. After each steps, 1, 2, 3, 4, after each steps, the message M arrives to its destination. How to calculate the time needed? The time needed is the total time needed to send from here to here is the sum of the time needed to send the message from here to here plus from here to here plus from here to here plus from here to here. So the calculation of this using this equation will be multiplied by the number of hops. This is the time needed to send the message. So H times latency plus the size over the bandwidth. This is the first way. It is the easiest way, but sometimes it is not really efficient, because if we check the second way, we find sometimes that it is better in terms of time. What is this second way? This second way says that we can use a pipeline technique, يعني data flow parallelism, to split the message into queue packets. So we will split the message into queue packets. M becomes M1, M2, M3 حتى MQ of the same size. Of course, we are simplifying as much as we can. We are considering that the message M is split into M3, M2, M1 with the same size. We are also considering that the latency is the same from here to here and from here to here, and etc. We are considering that there is no other overhead to count, and that the bandwidth is constant here, 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 etc. We are considering so many things to simplify the calculation, because the aim of this chapter is to illustrate the idea, but later in practical you have to take consideration of the different bandwidth and the different latency and other overhead costs need to be taken into consideration, etc. So here let's go back to the second alternative, splitting the message into multiple messages. Here we split it into 3 equal sub message, and we will send this from PI to the first hop. M1 will be here. After this we'll go here in the second step. At that time M2, the second part of the message, will be sent from PI to the first hop. In step 3, the third part of the message will be sent to the first hop also. At the same time, the second part of the message will be sent to the second hop, and the first part of the message will be sent to the third hop. In step 4, the message M1 will reach its destination. So M1 مشى شد اثنينته وصل ال M1. We have now M1 in the destination, but we need step 5 so M2 can reach the destination. We need step 6 so that M3 can reach destination. Now we can say that we have M here, because we have M1 and M2 and M3. This is the way how to send the message using the data flow parallelism or using the pipeline technique. Don't forget, our objective is to calculate the time needed to send the message M. So let's break it down. The time needed to send the first part of the message M1 كيما حسبناه في السلايد اللي قبلها is the same equation like this. This is the time needed to send only M1. The second packet, M2, will need the time needed to send M1 plus the time needed to send M2. Of course, we will not count the number of hops again. The number of hops is counted one time. خاطر وقت اللي M1 تعمل في الهوبس M2 also تعمل في الهوبس except the last one. وقت اللي M1 وصلت there is no M1 here, so M2 need to consider the hop, the last hop. That's why we can say that T1 plus the time needed to go in the last one is the time needed for M2. Another way to express this is the time needed to send the packet 1, this is the time needed to send the packet 2. H here and 1 here, we can formulate it like this, H plus 1 will communication time in general. The third packet M3 arrives at PJ at the same time, نفس الشيء. T3 هي T2 plus the last one. If we want to calculate M3, it is the time needed to send M2 plus the time of the step 6. Again, we can organize it in this way, H plus 2 multiplied by the time needed to send only one packet. There is something important I didn't tell you about here, is that there is a difference between this in the pipeline context and the old one, this. The difference is that this is the normal one. In the pipeline it will be like this, L plus N over BQ. We added the Q على خاطر we are not considering the N but we are considering N over Q because we are splitting the size of the message into Q parts. That's why we have always Q here, Q ديما تتبع فينا اللي هو the number of parts of the original message. So if in the third part we have this, we can generalize it and we can say that with each new packet we are adding an additional L plus N over BQ to the previous total time. Par récurrence, the formula for the total time T to receive all packets is given by the time TQ when the last packet arrives. Par récurrence نجمو تشوفوا لنا اللي T2 هي H plus 1 times نفس الشيء, T3 هي H plus 2 times نفس الشيء. So in general T هي H, chain relation between 2 and 1, 3 and 2 is always Q minus 1. ديما 3 minus 1 is 2, 2 minus 1 is 1, etc. So Q minus 1 here هي اللي ديما نزيدها لل H ونضربها في نفس الشيء. نلقاو this is how to calculate the time needed to send a message M divided into Q packets with the same size using H number of hops, number of bridges, number of intermediates. You can see here that the time needed to send the message depends on the queue, and the queue is our choice. If we split the message into two sub-messages, we will have a t. If we split it into many sub-messages, we will have another t. So our aim is always to optimize the t. How can we optimize the t based on the queue, the number of packets? يعني the question is, what is the best t, the minimum t, or the question is, what is the best number, the best queue that give us the minimum number of t? In other words, how can we minimize t by choosing the best queue? How can we split the message in the best way to gain time? This is what we are going to talk about now. The aim is to optimize t through optimal queue. This is our t. We can take the derivative of the total time equation with respect to q. نعملو الديريفي متاع هذه بارابور ا q. نلقاو q0 اللي هو this one. To find the optimal q we're in here, we set the derivative بعد ما نحسبو derivative نحطو equal 0 and solve for q. We find that q is minimizing the derivative when it is racine de h-1 fois mb sur l. We can see here لقيناه number of packets, the optimal number of packets. If the latency is high, so no need to split the message into many packets. شوف latency وين جاتنا في denominator. So we can say as much as L is high. هذه high شنو معناها؟ معناها هذه باش تكون أقل، الكبر متاع هذه ديما يصغر هذه خاطر جاية اللوطة. So we can say as much as L is high, as much as Q should be minimal, because splitting the message into many packets we will use the latency so many times, and if the latency is high, so the number of packets should be minimized على خاطر to avoid using the latency so many times. At the same time, if the bandwidth is high, معناها عندنا bandwidth كبيرة, we can take advantage of splitting the message into many packets. If the number of hops is high also, and if the size of the message is high, these three factors, if they are high, this will contribute in increasing the number of queue. But if the latency is high, the queue should be decreased. Of course, in all cases, there is an absolute optimal T that we cannot exceed. اللي هو the depth of the parallel calculation. The depth is defined as the length of the longest chain of dependencies present in that calculation. وشفنا هذا في chapter 3. This is an example اللي يحسب ال root of polynomial عادي ax carré plus bx plus c. هنا باش نحسبوا الدلتا we need 1b. We need also b carré. We need 4a. We need t2 اللي هي 4a نضربوها في c ومن بعد t1 minus t3 b كاري موان 4ac لقينا b كاري موان 4ac وقتها وين لازمنا نعملو لها الراسين كاري متاعها. so this is sequential يعني we have some instruction that can be done in parallel like t0 and t1 t0 and t1 and t2 t7 الراسين الاخر 2a هذوما الكل can be done in parallel but t3 cannot be done only after t3 هي dependent on t2 so t3 cannot be done only after t2 t4 cannot be done only after t1 and t3 t1 and t3 هذوما الزوز يلزمهم يخدموا باش تخدم هذه. so there is a dependency and the total time t مهما يكون optimal cannot exceed the depth of a parallel calculation. هنا استعملنا 4 processors ولقينا للوقت 1 2 3 4 5 6 units of time with 4 processors. What if we use only 3 processors? Let's use 3 processors here and try to find the optimal time. Again 1 2 3 4 5 6 it is 6 units of time. If we use only 2 processors 1 2 3 4 5 6 units of time, so 2 processors and 4 processors gave the same time, so it is waste to add more processors because the length of the depth is controlling us. كيفاش نطلعو depth؟ نجمو نعملو a graph dependency. This is t0 t1 t2 and t7 they can be done in parallel but the t3 depends on t2 t4 depends on t3 and t1 t5 depends on this all of them t6 depends on this r1 راسين يعني solution depends on t6 and t7. If we have only one processor the time needed is 9 because we will execute 1 2 3 4 5 6 7 8 9 instructions sequentially. If we have 2 processors now we can gain time to 6 units of time, but after the 2 3 4 5 etc processor we will always keep the same time. So the best parallel time is the length of the longest path in the graph dependency. This is what I wanted to say.